Somebody's intentionally trying to keep the logo. What are we talking about today? Oh, so I get ahead of myself. Good morning. What are we talking about today? What are we talking about today? Some concerns were expressed by those of us who are being held accountable for each other with the timeliness of arrival. It would be awesome if we all showed up on time for the class as an act of courtesy and respect for our classmates. Does that sound good?
Yes.
Perfect.
I'm sorry.
You're a repeat offender as well.
I'm a bad driver, okay? I'm doing my best.
You're not a bad driver, you're a slow driver.
Exactly.
Or you're not a bad driver, you're a great driver, you're a bad leaver of your house on time.
No,
Is that
I
it?
leave early.
What happens between here and there?
I'm a bad driver.
So what happens?
I drive so slow and I stop way before it's
She's a
even.
safe driver.
So yeah, that's what I'm thinking. Is like that means you're a good driver who leaves too late.
I leave 45 minutes early.
It's not enough.
Really?
Are you getting here on
It's only
time?
20 minutes.
Are
from
you
my
getting
house.
here on time?
No.
It's not early enough.
I'll leave 1 hour early. Or I'm gonna get better at driving.
Drive where you're most comfortable. Drive as you are most comfortable, but give yourself enough time to get here on time.
I will.
Because a good question was asked. It's like, so if the people come in late, should we help them?
With exception.
You know, so we want to make sure that we are showing up, representing how we want ourselves to be seen in this world, right? You don't want to pay attention to the least, the absolute least. It's like the thing that means the least to me in terms of interacting with other people. What they say. What means the most to me is what they do. So let's make sure that our actions reflect our intentions. And I love when we say that we're going to do a great thing and we're going to like make sure that we're kind of, it's like I love hearing that. I hope it happens, but I'm not going to pay attention to it until it does. Why? Because I said a lot of bullshit in my day that I did not do. It's like, yeah, you know, you're recognizing this difference between stating intention and living intention. We want to live it. The words are not quite enough to get us there. So drive as safely as you can. I don't want you to shave your driving and put yourself in danger, but we might want to build in some accommodation around it to get it to go. What are we actually talking about today?
Well,
Right. What did we do? We ended up with, we finished up lipids. We're going to move into amino acids, right? And I remembered that over the last day or two, we have not yet, I don't know if I need to go into it or not, the difference between cis fats and trans fats and why oils are room temperatures and other fats like butter and Crisco were not. Yeah, I think there were some questions in the chapter about that, but I don't think we actually ever talked about it. Did you want to have a 5-minute on that? You know, and I think it's not a bad idea to have a little bit of a chat about that because we hear about trans fats in a dietary way, and there's some baggage associated with like, don't eat too many trans fats because they're bad for you. Have you heard that? Like trans fats bad? Cool. So because it is a word that you hear in regard to fats and lipids, not a bad idea to give it a proper shake for a few minutes to talk about what we're talking about. What do you think? Yeah, you're sitting in literally the front of the middle. You can't escape. I see you every day when you're in here. So we'll talk about that and then we'll move on to proteins. So I'm not going to draw the whole triglyceride up here. I'm only going to draw like the top part of a fatty acid. Can you draw me the top part of a fatty acid? Can you?
No.
Okay.
I mean, I don't know how, but
Awesome. Okay, so I love your answer because it wasn't really you, it was can you. Who can draw the top part of a fatty acid? Like who could do it?
are we allowed to use our notes?
You can use, like, how would you describe a fatty acid? The top of it, the very top is what? The top part of a fatty acid was literally up here like 10 minutes ago. It's a carboxyl group. Yeah, it's like, raise your hand if you know how to draw a carboxyl group. You literally just did it on the. You want to draw me a carboxyl group?
Me?
Yeah. If you can't do it with chalk, you can't do it.
Okay.
You don't need to take your notes, do you?
No, just in case we miss something.
Security
Yeah,
security notes. Look at that. Oh, you can use any color you'd like.
No, I want to try this one because I tried the little.
A little nub.
Yeah.
Yeah, that's nonsense. Great.
Doesn't it go?
Yeah, so that's just like the top part of it. So that's the carboxyl group. So then it will just be. Yeah, you can draw you can draw like 3 carbons down from that if you want to.
Like that? I just want to make sure that's what it is.
Do you want to make sure or do you want reassurance?
I want reassurance.
Can we reassure this poor? Perfect. You feel reassured?
Yeah.
Awesome. And it just keeps going down, right? So when we like draw fatty acid, oh my God, fatty acid, I wonder what it is. Like draw a carboxyl group with a bunch of carbons coming down off of it. It's like, oh, I can do that. So let's not get caught up in the fancy names of things. When we talk about a fatty acid, all we're talking about is a carboxyl group with a bunch of carbons coming down off the bottom of it. If we're talking about triglycerides or phospholipids, there is like 16 to 18 carbons down with this. So a long carbon chain, about 16 or 18 carbons long. Traditionally, that's just trivia for when you're on Jeopardy. Good. When we look at this kind of stuff, and this is a good lesson for all biologists, I think, and chemists, when you're looking at this, we must keep in mind that we are drawing these atoms on a 2-dimensional surface, right? In fact, they exist in 3-dimensional space. So these look like right angles, like perfect 90-degree angles. On one plane they are, but when you start to like rotate this in 3-dimensional space as if it was a 3-dimensional thing, those right angles are going to turn into different kinds of angles because it is actually doing, another way to look at it, it's kind of doing this kind of thing. And because when you think about it, a carbon with 4 bonds that we have going like this, 2 of these, are coming at you, and 2 of them are going away from you. So 2 of them are going out in this direction, and the back 2 are going out in kind of in that direction. It's more of a 3-sided pyramid than 90-degree geometric angles, correct? That's actually sort of important for this. So if we are drawing, but so like we want to remember that. But if we're drawing just a carbon chain kind of going down, occasionally we get double bonds that show up like that. And so when that happens, if we only can put 4 covalent bonds on a carbon, we have to say, okay, we can't actually put any hydrogens on this, right? Because it's like there are no covalent bond spaces left for hydrogen to occupy. You with me on that? So if you wanted to, through chemistry, you could actually put more hydrogen bonds on here if you broke some of these. So if you broke this bond right here, you could put 2 more hydrogens on. But if you are going to have this bond, then 2 of these have to come off. Valence electrons, standard covalent bonding theory, correct? Good? Does that make sense? because we could put more hydrogen on here, this fatty acid is unsaturated. It's unsaturated. These unsaturated fats tend to be oils at room temperature, liquids at room temperature. It's unsaturated with hydrogen. It's hydrogen unsaturated. If we broke all of these bonds that are doubles here, put a bunch more hydrogens on, then we would say it is a saturated fat, and it would be more of a solid at room temperature. Go ahead.
What does it say about the H plus under unsaturated?
It's a little shorthand with, so the W with the, so the saturated solid is saturated with hydrogen. So when we're talking about saturated and unsaturated, we're talking about, does it have all the hydrogen you could theoretically cram onto it? In this case, yes. If you have double bonds, the answer is no.
If you have double bonds, it's saturated.
If you have double bonds,
It's unsaturated.
it's unsaturated. If you have only single bonds all the way through, it is saturated and tends to be a solid. And this is why. Can I erase this? Are you still drawing, looking? This good?
No.
Use your inside voice. Very exciting to watch me put molecular models together. Just remember, these are in here. Somebody go to Nova Day yesterday? There were a bunch of people outside doing, there was hot sugar and stuff to do, yeah. There was somebody out there that was making balloon animals.
Oh,
Anybody get any of the balloon animals or the balloon hat or the balloon stuff? I was taking the big long balloons and you fold them into stuff. Stuff like dogs. You can do the same thing with molecular. So everything about it, when I this dimensionality kind of thing that I was talking about, here it is. You know, this is a saturated fat. It is. It's like if we draw this, we're going to see it from this side, and it's going to be 90-degree angles all the way down because we're projecting. In truth, it is not 90-degree angles. Correct? So it's like when we're actually looking at the thing as it exists, we want to appreciate that we're drawing on a two-dimensional board when we draw these things. Okay? So this is the same thing as that here. It looks different, you know, because 3 versus 2. Awesome. So if you want one of these carbon chains to be, they're never going to be straight, but if you want them to be as straight as you could make them, you would have a saturated one. This is why the saturated fats are going to be the most solid at the coolest temperatures. So these are your butter, these are your Crisco, these are your lard, these are your, sums are up, doesn't it? Right, these are your saturated fats right here. When we look at oils and things like that, and we start putting in these double bonds, you're not going to have a double bond that looks like that on a two-dimensional projection. These two bonds here that go to this next carbon down, geometrically, they act like one, right? Because they're kind of paired right next to each other. So the thing is really going to look more like that. And then we could have like carbon, carbon with the hydrogens coming off. And you get these, what we call, sorry, fetishists out there, kink, right? You get these kinky tails coming off of these things. They're into all kinds of weird stuff. Have you ever seen all the pictures of Mary Magdalene? Always seems to be looking at Jesus's feet, right? It's typical in the paintings. It's like, is that the first foot fetish ever represented in history or what? So we get these kinky tails that show up in these fatty acids. And when you have these kinky tails that show up, we get more angularity within in the chain. And if we're talking about a triglyceride, you have three of these tails coming off of a glycogen molecule. They're going to start interfering with each other. If your triglyceride looks like that, they can pack very closely. If your triglyceride looks like that, they're not going to be able to pack as tightly with each other, right? They're going to be literally held apart by the kinky fatty acid tails, and they're going to be more liquidy. And the more unsaturated you tend to get, the more double bonds you tend to get, the kinkier the tails tend to be, right? The more interference you get with the things over to the side. So what happened in the First World War, remember that? First World War,
1914.
yeah, 18, 20, 20, like around there, give or take. First World War, just about everything, and the second, that could be sent to Europe to feed troops was done so, including most meat products and things like that. So that's where like Victory Gardens started to like grow as many of your own vegetables as you can. And like all the fat, all the lard, all the animal products were sent to Europe to feed troops as best they could. So here we all are in the United States trying to make a pie and pie crust, but we have no butter, we have no lard, we have none anything else. So the scientists said, how can we make a plant-based oil like canola oil or olive oil act like a saturated fat? So how do you turn something that looks like, this is beautiful, I'm gonna erase it. Both can be true. How do I take something that looks like this, which has this big kinky tail, which is going to be an oil? How do I turn this into something that looks solid at room temperature? And then it's like, well, what do I have to do? I need to shove some hydrogen onto it. I need to start making it act like a saturated fat. So I'm going to get a high pressure, high temperature acidic solution, and I'm going to shove it onto this thing, and I'm going to try to hydrogenate, break as many of these bonds as I can, and hydrogenate them. And so it's like, bam, got one. So I took this one out. This got hydrogenated. Perfect. And I have straightened out the bond. I broke it and I shoved it down in the downward direction through hydrogenation. And now I have a straighter fatty acid tail. I don't do all of it. I just do as many as I can to get the properties of lard or butter. So what I have created is a partially hydrogenated vegetable oil. Partially, so if you've heard of partially hydrogenated vegetable oils, they're vegetable oils that come from plants that are hydrogenated by an acidic solution under high temperature to make them act like a solid fat, make them act like an animal fat, which is kind of neat. You've heard of partially hydrogenated vegetable oils? Look on the back of what you eat. Like cookies, cheap pie or cake, right? Things like that. The perfect example of this is Crisco. Like you've heard of Crisco?
Mhm.
That's what happened here. It's a plant-based oil that was hydrogenated into something that's solid at room temperature. Pretty neat, pretty neat. This is now what you refer to as a trans fat. And the trans refers to what's happening here. Because there is another arrangement I can make when I break that double bond right here. Or I could do this. There's my carbon, right? I make it even kinkier than I made it before. So when you have a carbon-carbon bond that is a double bond, if the hydrogens are on opposite sides of the chain, it is a trans fat. If the hydrogens are on the same side, pushing it even to a bendier, kinkier, more curvaceous fat than you had before, it's called a cis fat. So cis, trans, cis, trans. Dietarily, we want the trans. When we make them, sometimes they break and get even kinkier. Those are the cis fats. They're even more liquidy. They're even more liquidy. What do you think?
So just to make sure I understand, the difference between a cis fat and a trans fat is whether or not the hydrogen atoms are on the same side of the strand?
Yeah, if they're on the same strand, it's a cis. And the consequences of that are that this gets even bendier. However, if they're on the opposite side, it straightens the chain. So if anybody takes chemistry, like biochem or organic or anything like that, you will hear the word cis and trans all the time, in exactly this kind of context. Same side, cis, opposite side, trans. Trans fats, solid, cis fats, liquids. Both unsaturated. Born of the industrialization process of the war effort. Sylvia, that makes sense? Huh?
Yes.
Yeah, it does. You okay with that?
I can live with it.
Nice. Nice. Love it. Perfect. Like Star Trek. Anybody watch Star Trek? Star Trek fans? Yeah? Star Trek versus Star Wars, who wins?
Star Wars.
Star Wars is fantasy, by the way. It is not science fiction. That's no different than Game of Thrones. If you're a Star Trek fan, however, awesome. I mean, debates rage on Star Trek versus Star Wars, right? Which one is like, let's say, better? The call letters of the Starship Enterprise? Oh, yeah. And the backbone of, so like the Enterprise is nothing more than like a big amino group flying in space. Right? What's the R group? Anything can go there. Got me so excited. two monopeptides, two amino acids in full glory, whatever they might be. There's this handout that I gave out twice. This one has the 20 amino acids that we use in our bodies to make all kinds of neat things. Is there some way that is fancy that you can think of where we can make these two monopeptides into a single dipeptide that is joined? How can we make a large chain? We can do another one. How can we join these together into now what would be a tripeptide? Have we learned any reactions that do this? How did we attach carbohydrates to each other? How did we attach fatty acids on the glycerol? How do we attach any of these things? We talked about it a very long time ago. I think it was Tuesday. Is that, if you're gonna raise your hand, properly raise your hand with some, go for it.
The OH and the H, is it hydrolysis, like you can make H2O with water? Like, bond them?
I don't know what you're talking about, show me. This is a way to make sure nobody ever raises their hand again.
Yeah, it works.
Perfect.
Like, this and this, H2O.
Do it.
Huh?
Do it. You have an eraser right there. That's okay. And what do we do with that water? Will help. Where does that water go?
Dehydration.
Work together. Class, if you can't do it with chalk. Class, if you can't do it with chalk, can't do it.
I know it's dehydration. So this. Oh wait,
Carbon?
no. See, like I link that with that.
What are we supposed to do?
Supposed to, you have 3 amino acids, you're gonna try to make one long chain out of them.
Right. Okay, class. How do you, basically, I said dehydration, but how would that look like to be able to link that? Something OH.
I don't know how you would draw it, but just like look for the H's and look for the O's.
It's like the one at the top as well.
Yeah, but like.
On my notes for like the fatty acids, I know this is an amino acid. It's like you draw it at the top with like the NCC, but I don't really know how you would.
Like,
please don't make me. Please don't make me. Okay, we can try. I guess. This might be completely wrong, but
I'm fucking kidding.
do my best.
I work this
Okay.
down.
Right.
So I don't know how to draw that to look like something like.
I saw this, that's why I said like, you know,
Okay,
what'd you say?
like it's just all of that.
But that's if there's an OH in the bottom, like this, right? Right here. Oh.
How many O's? Oh wait, and this one.
Wait, what is
1, 2,
that?
3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4. How many waters can I make?
Wait, if you just take this and pass that over here, isn't that H2O?
But how do we connect the three?
Never mind. What?
We have to connect the three. Man, what does that?
That's not in my notes.
Get the water out.
Oh, because we okay.
Because if you're gonna be,
that goes over there.
if you're gonna be
Hydration.
dehydrating, the water has to come out.
Yeah, I don't know what you're gasping for. I don't.
Wait, if it takes out if the H2O gets out, wait, but then you wouldn't make that H2O.
We're left-
because you don't.
So
Wow, this is a lot.
we would have 5 of these with 1 extra hydrogen.
Wait, I don't think it's the like he's gonna do the same thing over here.
We can just connect those.
Yeah,
So you'll make this H2O. Ow!
Is it
yeah.
okay? And then just
But then
a bunch of H2Os over there.
How many in this case?
oh four.
Two.
Wait, what?
2.
Wait, I thought it was H2 and then H2 that we're removing, right?
Yeah.
Oh, so this one's gone too.
Because we are
Hydrating. Wow.
Yeah.
We're doing like all the math.
Good job, yes.
I don't know.
Good job, good job.
I don't know.
It's okay.
3 people in this class will never forget this. Or because they will be talking about it with their therapists for years to come. Right. So functional group, the whole thing is a carboxyl. This part of it is a hydroxide group. And you have this hydrogen, you can just take some water out, shuffle the bond. You can do that over here as well. And shuffle the bond.
So you make the carbon and the nitrogen attach to each other.
You can do the same thing with carbohydrates. You take one of the H's and the hydroxide, take the water out, and this time you go through oxygen, one of the oxygens stays behind. So you end up with something looks like that, plus the water molecule that comes out. Remember this? A little bit? When we have a glycerol molecule, right? And a fatty acid, we can take these 2 H's and that O, make some water, and what we're left with is this fatty acid with the oxygen left behind. So in this case, we're taking 2 hydroxys, an OH and an HO, taking them out to make water, and the leftover oxygen is the bridge. We do this with carbohydrates. We do this when we attach fatty acids. When we attach amino acids, the water is the only thing that's there because we don't have a hydroxide on the nitrogen because it's an amino group, right? So the carbon bonds straight to the nitrogen. Thusly, go for it.
So when we're attaching bonds, we dehydrate them?
When you take a lot of things and bond them together to make large polymers, you dehydrate.
Yeah, okay.
If we wanted to split them, you put the water back in, which is, say your answer proudly.
Hydrolysis?
Without asking me a question, don't ask me an answer, tell me an answer. I'd rather you tell me an answer be wrong than ask it and be right. You're up talking at the end, which makes it sound like you're asking me the answer.
Oh, hydrolysis.
You still did it, try it again.
Hydrolysis.
Make your pitch go down at the end.
Hydrolysis.
What'd you have for dinner last night?
Pasta.
Pasta?
Yeah.
Pasta.
Pasta.
Pasta?
Pasta.
What is it? So when you add the water back in, it's to split.
Hydrolysis.
Perfect. Tacos? Pizza? Pizza. Questions? Thoughts? So what kind of bond is this then? This is what we call a peptide bond. And this is now a tripeptide. And yes, the actual background of it is now just like N, C, C, N, C, C, on and on and on, with R groups coming off the only carbon that is not an R group or a functional group. So, go ahead.
How do you spell what you wrote at the top? But that was a tripeptide, right?
Yeah, because there were 3 amino acids in it, so you'd say it was a tripeptide. So tripeptides are joined by peptide bonds and dissolved in your stomach using the enzyme pepsin, and alleviated by Pepto-Bismol.
That sounds so gross.
It is
It's
gross.
so
The
good.
color is bad, the texture is bad, the flavor is bad. No, thank you.
It's like bubblegum.
It tastes like ass is what it tastes like. Horrible, like minty bubblegum or something.
Who in their right mind would make freaking medicine to make bubblegum?
To review, we have carbohydrates. Correct? We can dehydrate this into something like that, plus water. And this is referred to as a, glycosidic bond or a glycosidic linkage. These are 2 monosaccharides, and we have made 1 disaccharide. Making a table. So what do you think about that?
So the arrow is dehydration.
Yes. What I could do to make it even fancier, though, I'm not changing anything. We could say this is. What about the arrow that goes the other way?
Hydrolysis.
Hydrolysis. And who's going to take Bio 102? Anyone? This hydrolysis, done by the enzyme called amylase. It's in your saliva and in your pancreas. This digestion we can Bio 102, so it's on my mind. You don't need, this is Bio 102 info, but if you're into trivia, there you go. However, when we talk about proteins, which are long chains of amino acids, we make a peptide bond, and we go from 2 amino acids. You wouldn't really call them monopeptides. And you would turn them into a dipeptide by making a peptide bond. And breaking it this way using pepsin hydrolysis to break it. Dehydration to make it. I'm sure all of this is very clear.
Yeah, totally.
Absolutely.
You got to be in the flow, man. You just got to stay in the flow.
Your flow's like a raging waterfall.
I love that. I love that. Thursday, here's a fire hose. So you're sort of seeing dehydration and hydrolysis as being opposite drivers of a reaction, kind of moving stuff back and forth a little bit. That's either fear, terror, or fatigue.
I'm just like kind of confused, like where is it? Like, is there like a separation at some point?
Question, what's the it?
Do I have to get up?
No.
Okay. So
Start your
right
pencil
there,
at it.
we have the peptides, right? And then it goes,
Amino acid.
okay. And then it has, that's pepsin.
Pepsin is the enzyme that,
Okay.
so pepsin is going to drive it this way.
Okay, then what's the squiggles underneath the hydrolysis?
These are arrows.
Okay.
I can't believe you can't see how clearly that is. You can almost draw those chemical equilibrium arrows a little bit, you know? So this would be hydrolysis drives it. My arrows are the wrong way. Hydrolysis breaks it, and dehydration makes it.
Dehydration breaks it, right?
Hydrolysis breaks it,
Okay.
dehydration makes it.
So when you're using
Dehydration, hydrolysis. Dehydration, and water comes out, put water back in, hydrolysis. What's going on?
so
How are you today?
Good.
Awesome.
when you're doing like working with proteins and like peptides, the hydrolysis is considered pepsin.
The enzyme that makes the reaction happen is pepsin. So your stomach is so you eat a bunch of meat and your stomach produces pepsin, which hydrolyzes those polypeptides into monopeptide amino acids that are smaller.
So just to clarify, when it's peptide, that's when dehydration is happening. How would you word it? Like,
What are we trying to add? What are we trying to sort?
I'm trying to sort out what specifically peptide and pepsin.
Pepsin is an enzyme that makes work happen.
Okay, then what is pepsin?
The peptide is the bond. So this is a peptide bond.
Peptide is a bond, and then
Yeah.
pepsin.
So
is
the
enzyme.
bond was like glycosidic linkage,
Uh-huh.
peptide bond.
Mhm.
When we dehydrate nucleotides to make long DNA chains, we're going to make phosphodiester bonds. So like the nature of the macromolecule determines what that bond is called and what the joiner is. So, and when we make disaccharides out of monosaccharides, we leave this oxygen because we make the water out of 2 hydroxy groups, right? So H, 2 H's, 2 O's minus 1 H2O leaves you an oxygen left, correct? So, and there it is, With the amino acid, we have a hydroxy group and just a lone hydrogen. So we don't have that extra oxygen around to be the joiner. So you end up with this direct bond between carbon and nitrogen, which is called a
Peptide.
peptide bond. If, what do I talk about nucleotides? It's like if you use an actual phosphate group in one of those wonky oxygens to do it, you leave the phosphate group and you do a join. That's the phosphodiester bond, because it's just this is getting ridiculous at this point, complicated wise with how DNA latches up. Brooke, you good?
Yes,
Cool.
thank you.
This is why I ordered a large eraser. For exactly this reason. If the chalk doesn't make sense, I'm sure it makes even more sense when I'm standing in front of it as I'm drawing. So what we're talking about is the amino acid as the macromolecule, and we can all draw those already because we did so on the back of what you turned in today, yes? It's a carbon with a amino group, or carboxyl group, a hydrogen placeholder, and whatever. So almost the entire thing is functional groups or placeholders and other wonky stuff, right? So whenever I say, how do you draw an amino acid? It's like, well, draw a carbon, attach an amino, attach a carboxyl, drop anything you want off the bottom of it, take up the other space with a hydrogen. Why do we keep harping on functional groups? They're everywhere in this. It's like the best thing you can do to be a good chemical biologist is those functional groups are everywhere. And the toolkit that they represent, which is awesome, is that they are ample, proper, multitudinous fuel for dehydration and hydrolysis reactions. These functional groups are functional groups for a reason. They are very friendly towards dehydration and hydrolysis. And if you are nothing else, you are a polymer of a bunch of stuff interacting with each other.
What is that word right under?
This one,
Yes.
placeholder,
Okay, thank you.
it's like we have an extra valence electron, so we'll put a hydrogen on it to make it take up space. Was that your
That was
question
my
too?
question.
Yeah. I get excited, my handwriting goes to hell. So amino acids. We find them in 2 forms when we see them. They can be structural. When they are structural, we call them proteins. And it's when amino acids polymerize into a long chain. So you can take a bunch of amino acids, a couple thousand of them, turn them into a long chain. They're going to fold into 3-dimensional arrangement. You may have this for whatever reference that you have it. You don't need to get it out. Look familiar? So, grab 100 of these, line them up, dehydrate them. You get a polypeptide that is 100 amino acids long and 99 molecules of water come out. Good? If you just take a protein and read down the line, okay, it's leucine, isoleucine, valine, proline, tryptophan, valine, glycine, just reading off down the line what amino acid you get to, that is referred to as primary structure. It's nothing more than the sequence of amino acids. Just read them from left to right down the line. As the ribosome, we'll talk about this next week, is attaching these amino acids one onto each other as you go down the line, it will start to form into different kinds of structures as it's being produced. It is called secondary structure. It will either form coils, so it'll turn into like a corkscrew kind of looking thing. This is referred to as an alpha helix, or it will form folds where it'll go like that. It's called a beta pleated sheet. Like those fancy room dividers, you know, they sort of accordion out. It's kind of like that. Once you have all these coils and all these folds that have formed in this emerging structure, then you get tertiary structure, and that's where it actually turns into a three-dimensional form. It'll actually have three-dimensionality. And sometimes that's where it ends. You know, sometimes it's like, great, you got this protein, three-dimensional, it's doing its thing, that's fantastic. Sometimes, not always, you have quaternary structure, which is several tertiary molecules together, usually stuck together using weak bonds like hydrogen bonds and things like that. A good example of quaternary structure is hemoglobin. You've heard of hemoglobin, yes? Where do you find it? It's in your blood. It's in your blood. The hemoglobin molecule is quaternary structured. It consists of 4 tertiary structured proteins. 4 of them. So it's like you make these 4 different components of it, and they're all self-contained and everything is fine, and then 4 of them interact with each other to give you one quaternary structured hemoglobin molecule. You have some molecules in your body that are stretchy. Things like some ligaments, maybe some occasional tendons, but like your skin is stretchy if you're under the age of 30. Once you get over the age of 30 or 40, your skin gets less stretchity. No, I'm going with stretchity. It's like right now, it's like you can pull it, it kind of springs back where it's supposed to be. The older you get, that springiness sort of gets a little, well, it just doesn't get as springy as it used to be, right? You start to get the breakdown of these collagen molecules in the skin. So there are 2 things that you can do about that. Well, 3 things you can do about that. You can Botox, right, and inject, toxins in your face, which also I hear works well for migraines. You can get collagen injections, so you can boil down like the bones and hooves of cows and horses and things like that, and inject that into your face. Or you can come to terms with the fact that gravity always wins in the end. It's like, well, it's part of my awesomeness. Very cool. And when we use one hot one, when we think about what gives collagen its properties is its stretchiness. It's springy. It's like a spring, right? What kind of secondary structure do you think you see in collagen? The beta pleated sheets or the alpha helixes? That look like that. Which one do you think you'd find more of in collagen to give your skin springiness? These or these? Yeah, totally the springs. That's what springs do, right? So we really are talking about this relationship between the physical structure of this thing and its properties. With collagen, the things that make your skin and your hair springy and all that kind of stuff is actually quaternary structure. It's made of 3 alpha helix strands woven together, literally braided. So it's like, it's made out of stretchy things that by their structure are again another level of stretchiness. So it's like, no wonder it's so stretchy, right? The secondary structure is mostly coils, and the quaternary structure is braided coils. So it's gonna be springy. It's gonna be springy. It's like a direct relationship between what it looks like and what it does. Question?
So you said, well, it's kind of two questions, but they're both about collagen. So like, if you take collagen pills,
Yeah.
does that like help? And what does like lotion do?
I don't know. It's like, because people like to take collagen, it's good for your knees and all that. I'm not sure if that's true. It's a good protein source and it provides like all the amino acid raw materials for making collagen. I don't know if you can take collagen directly out of your stomach. And it's like, you go into this part of your, collagen in the stomach. I have a hard time imagining that translates into that collagen in your face, or in your knees, but it's going to get broken down by the pepsin in digestion. But it's like, but the amino acids will be intact. So maybe it just provides so many raw materials that you get more of it produced maybe, or easily. You don't have a deficiency of anything. But it seems hard to believe that you could take a collagen pill and that collagen is going to end up here. I don't think it sort of goes that way. Like the collagen cream, though, I mean, that can give you a little springiness. I don't know if that's because of the collagen or just from
I
moisturizing.
mean, just like lotion, like a lot of people who moisturize from very young, like their skin retains that springiness. Does that have anything to do with like our actual like? I don't know. What's
It must. Yeah, it must. I mean, I do. I mean, I moisturize my face every morning because for many, I only started doing that about 6 months ago, and up until then, I didn't. Gasp, right? And I was getting like this kind of dry, flaky, kind of whatever, 50-year-old, 51-year-old man skin. And it's like, nobody wants that. So I get the Trader Joe's, sells it's not the Trader Joe's, it's the Burt's Bees facial moisturizer. It works very well. One component of a multifaceted skincare regimen that I engage in every morning for your pleasure.
This kind of like goes off the first question of like, say you take a pill that's like for your face or like you're trying to help your acne or something like that. How does it know? How does the pill know that it's working for your face? Like, I don't understand that.
The pill or your body?
Your body. Like, I just don't understand. Like, if you're swallowing it, how does and then how does it end up helping your face or anything like that?
It depends on what it is. Are we talking about like an immunosuppressant, like prednisone or something like that?
Yeah, something
Like
like
a steroid thing?
Yeah, just how does it like? I don't understand that.
Those can go in. So it sort of depends on what it is. So like with the collagen, you take a collagen pill, it's like, that's going to get broken down to amino acids and they can get repurposed somewhere else. The best thing to do would be to give the body some impetus for doing that, which would be a good thing. But other things like steroids, like prednisone, like we were talking about the other day, like the estrogen pills and testosterone or whatever it might be, the prednisone is a good example because a lot of times it is taken for like skin rash, skin conditions and things like that. It will go into the bloodstream, the actual steroid will, throughout the body and into the cells. And in those places where you have a lot of inflammation, it'll shut that shit down. Pretty good. And the added benefit is that you get like super emotional all the time and it's fun. It's like, you'll have beautiful skin, but you can't do prednisone for a longer term without consequences. Nothing like bad, but yeah. So the question is like, how do you target a drug to a part of the body where you want it to act?
Yeah.
That's hard. It's hard. And usually you just take the actual amount of whatever it is in the pill is way more than what this spot on my arm needs, but it's not just going to go here. It's going to go everywhere, So trying to target drugs towards locations is an emergent field in biotechnology. Crack that nut, you'll have a long and happy and lucrative career in front of you. Do it. You only need like 9 years of organic chemistry. You'll love it. It'll be a joy. Questions, thoughts, comments? Next week, we're gonna talk about DNA and we'll start cell structures and all that other kind of fun stuff. I will see you in about 15 or 20 minutes over in lab today. Did you get my announcement?
Yes.
Yes. I'm getting these folks in my Bio 102 class, and they're starting to get lazy already. It was only their third lab, and it's like a couple of them are like got a bottle of water and they're drinking it in lab. I'm like, nope. No, right? We can't eat in lab, we can't drink in lab. We can't have open-toed shoes in lab. And we don't want to wear mini skirts in lab. Or, clothes that is not safe with Bunsen burners around and all that other kind of stuff. So I will try to remember to remind us on Wednesdays and Thursdays that we have a lab day coming up. Might be helpful. The closed-toed shoe, though, is the killer. So I think everybody's good in here. Good? Everybody all right?
Yeah.
See you in a few minutes. 1, 2, 3. See you soon.
I am
Hey.
still a little bit confused with the
So a little bit confused.
peptide, so I understand how